Yes, good morning friends. Welcome to the lecture of functional analysis. In today's lecture, we are going to start a new topic of Hilbert spaces. Till now, we have seen the topic of Banach spaces. In detail, in Banach spaces, we have seen many theorems. It was a new concept related to complete nonlinear spaces. Norm we have seen, which is a generalization of a metric or distance function, right? In the similar fashion, in this chapter, we are going to see the generalization of a dot product. We know the product, we have studied the product right from the first or second standard. Product of two numbers to two scalars, right? Later, the concept was extended to the product of two vectors. And the product of two vectors was defined with the help of two concepts. One is dot product and another is cross product, right? Among the two, we are using dot product mostly because it is giving us the resultant as a scalar quantity, right? Now we are going to make the generalization of this dot product as an inner product. With the help of this inner product, we are going to have a generalization of the Euclidean spaces. We know what are the Euclidean spaces. Euclidean spaces are nothing but the vector spaces, right? In which we are considering the product of the two vectors by dot product. Therefore, we will generalize this concept of Euclidean spaces to the inner product spaces with the help of a definition of inner product, right? Therefore, before going to understand what is the inner product space, there is a need to focus on what is the inner product definition. Okay, before the definition itself, before the definition of an inner product, we will try to understand what is the need of an inner product. Okay, let me share my screen. I hope the screen is clearly visible to you. The topic name is Hilbert space actually, but before going to see what is Hilbert space actually, we will focus on the inner product. Okay. Therefore, the first definition we are going to study is inner product. Two different types of definitions we will have already is ordinary product, and write as a multiplication, and then dot product. Okay, what is multiplication? Is the screen visible to everyone? Can anybody tell me, is the screen visible? Is the screen visible?
Yes, ma'am.
Therefore, we will see what is the multiplication first. Multiplication is the concept we have seen somewhere in our primary education, right? Now, suppose I am writing a multiplication 2 into 3. Right? I am writing a multiplication of 2 into 3. How it is going to be work? 2 into 3. 2 into 3, we know it is equal to 6. But if I want to show how this is going to work, right? Can anybody tell me how the multiplication, as it is a real number, okay, as this is the real number, therefore we are going to work out this on a real line, right? Just wait. Okay. See, this is my real line. And if I want to find out the value of 2 into 3, right? How this is going to be? Okay, suppose this is a 2 unit distance. This is 0, 1 and 2. Therefore, this much distance is 2 unit distance. And what multiplication tells us? 2 into 3. That is 2 unit distance is taken thrice. Or 3 unit distance is taken twice. One of them we have to follow. Okay, here I will follow 2 unit distance is taken thrice. Therefore, here let me just mark those points. This is 4, 5. Here it is 3, 4, 5 and 6. Right. Therefore, this is a 2 unit distance. 2 unit distance. Once I have taken, let me take it twice and let it be thrice. Okay. I request all the students to join early before 12 itself. because it makes a disturbance to make them admit. It will be a disturbance. Okay. Therefore, here a 2 unit distance we have taken thrice. Therefore, what is the resultant? This is 6. Okay. Why this could be possible for us? Because both the numbers 2 and 3 are the real numbers, and we can evaluate this multiplication on a real line. Okay. Therefore, this is possible. But if we proceed further from a one-dimensional space to higher dimensions, okay. Therefore, here I will write this in R. Right now, on a real line, this is going to be possible. Now, if I am going to extend the same concept to R2, say, two-dimensional spaces, whether the same concept we can work out, no, this could not be possible for us. We cannot take a 2 unit distance thrice on an R2 space. Then what we should do? We should go for the generalization of a multiplication. Okay, we should go for generalization of a multiplication, and that multiplication we have defined with the help of a dot product. Therefore, here we will consider a dot product and we'll try to understand how the dot product is being evaluated. Why these basic things are essential? Because unless and until these are clear, you cannot understand what is an inner product, right? Therefore, what this dot product is, we know there are two different definitions of a dot product given to us. Okay, what is the first definition? Suppose x and y are the two vectors in the R2 spaces, then x dot y defined as mod x into mod y into cos of theta. This is one definition. Or suppose if I have two different vectors in an R2 space, say A and B, where A is defined to be the two tuple vector A1, A2, and B is defined to be another two tuple vector, say B1 and B2. Then we have defined this A dot B as A1, B1 plus A2, B2. That is the multiplication of the x coordinates added with multiplication of the corresponding y coordinates of both the vectors. We will try to understand how this is going to be defined or how this is going to be worked out. Can anyone know the reason behind both the definitions? Why it was defined as mod x, mod y cos theta, and why it is piece by piece multiplication of x coordinates and all? Can anybody tell me? You can unmute yourself and you can answer the question. Reason behind the two definitions of dot product. Yes? Can anyone answer? येईल सांगता कुणाला? Okay, let me explain. The first definition which we are going to take, x dot y belongs to R2, defined as mod x into mod y into cos theta, right? Now here, as we have studied, if the two numbers are on the same line, multiplication is easier. That is 2 unit distance taken thrice or 3 unit distance is taken twice. Okay. Therefore, in R2, what we are going to do, with the help of the trigonometric measures sin theta and cos theta, we will try to bring both the vectors on one line. Once it comes on one line, it will be easier for us to use the multiplication definition. Okay, let me show you how. Suppose this is mod x and suppose this is mod y. Okay, here let me call this is some mod x and this be some mod y. Angle between the two vectors be some theta. Angle between the two vectors be theta. Now what we want to do? We want to bring both the vectors together on a single line so that we can use an ordinary multiplication definition. Therefore, here there is an angle between the two vectors as theta. Therefore, either we have to take mod y on x vector or x on y vector. Now what we will do? What we will do here, we will drop a perpendicular from this point on a x vector, right? Then with the help of cosine measure, may I say this much distance will be mod y cos theta, right? Right now, what is cos theta we are defining? Cos theta is adjacent upon hypotenuse. If I call this distance, say E as some, if I give some numbering, say this is A, B, C and D, then this AC will be an adjacent side, that of AB will be an hypotenuse. Then this cos theta will give us AC upon AB. Okay, therefore what is AC? AC will be AB cos theta. But what is AB? AB is mod y. Therefore this is mod y cos theta. The distance AC is given with mod y cos theta. Now we have both the scalars mod x and mod y cos theta on a same line. On which vector line? On x vector line. Therefore now we will use a ordinary definition. Then what our ordinary definition says that mod x into mod y cos theta. Mod x into mod y cos theta. That is mod x taken mod y cos theta times, or mod y cos theta taken mod x times. One and the same thing. And that is what a definition of x dot y. Y cos theta is used. Okay. Is it clear? Dot product definition. Now we will see the another definition. This is called as a piece by piece definition actually. Okay, here I will just write A1, B1 or instead of A1, B1, it will be better for me to write AX, AY. X component of a vector A and Y component of a vector B. For BX and BX and BY. Okay. Therefore now what will... Yes? Is someone speaking? Unmute yourself. Everyone please unmute yourself if you want to talk. Otherwise mute. Yes. Now we will see how the definition is going to work, right? A is equal AX, AY are the notation I have used just to ensure that this will be X coordinate or X component of A. AY is Y coordinate or Y component of A. Okay. Therefore, again in R2 space, let us write this vectors as like this. Okay. This be a vector say A and this be a vector say B. Now we don't need any angle between the two vectors. We are going component wise, right? Definition says that it is AX BX plus AY BY. Okay. Now for A first we'll try to understand what are the X component and what are the Y component. If this is a vector A, if I just drop a perpendicular and an horizontal line, okay, this will be a vector AX and this will be a vector value AY, right? AX is X component of a vector A. AY is Y component of a vector A. Same thing we will do for B. Same thing we will do for B. For B, this will be my vector BX. And this, sorry, I should draw this by dotted lines. This is BX and this could be BY. Okay. Therefore, BX is X component of B, BY is Y component of B. Okay. Then as we have four different components in our hand, what is the possibility for the multiplication? The possibility for the multiplication is, here I will show you. Possibility for the multiplication is, first combination is AX, BX. First combination is AX, BX. Second combination is AY, BX. Third combination is AX, BY. And let us say last combination is AY, BY. If I just want to have the all possible combination of the components of the vector A and B respectively. What AX and BX will give us? AX is a X component of A. BX is X component of B. And hence a multiplication is possible. A multiplication is possible because both the components are on the same line. Therefore, with usual multiplication, this will be a having a scalar value ax bx, very similar to 2 into 3 is equal to 6 as we have written. Okay, now let us go for the second combination. In the second combination, ay is a component in this direction and bx is the component in this direction. Therefore, these are the two different vectors in different directions. Therefore, we will just use the previous definition. What the previous definition says that this is mod ay into mod bx into cos of theta, angle between the two vectors. But we know one component is along x-axis, another component is along y-axis. Therefore, the angle between them will be 90 degrees. And we know what is the value of cos 90? Cos 90 is 0. Therefore, this result, the multiplication of this, the resultant of this multiplication is 0. Okay, let us do similarly for the third possible combination. This is ax, x component of a. This is by, y component of b. Again with usual dot product definition, this will be mod ax into mod by into cos theta. Again the angle is 90 degree, therefore the resultant is 0. Therefore this is again giving us the resultant as 0. Now let us go for the last combination. This is ay and let this be by. Now both are on the same line along y direction, along y axis. Therefore this multiplication is very similar to the usual multiplication. Therefore we have a resultant scalar ax bx and here it is a scalar ay bx, and if I add all these possible combinations, middle two values are 0. Therefore we result with ax bx plus ay by. Okay, this is what an idea behind the dot product. Is it okay to everyone? Okay, therefore there are two definitions. One is mod x mod y into cos theta and this is piece by piece. I shown you both the concepts in a clear manner. Okay, now here in these definitions, nowhere we are using a complex number. This is what you can say a small lacuna in the dot products. Therefore, we are extending the product for the complex numbers as well. Okay, therefore the multiplication concept was extended. First concept was studied is multiplication, ordinary multiplication, which was later extended to a dot product. Now we are extending to the inner product. Now we are extending this to inner product. Okay, therefore let us try to extend the concept of dot product to inner product. Okay, now while making the generalization, inner product was extended, made or defined in such a way that it should follow all the properties. Therefore here I just want to show you the properties in detail. Okay, therefore here I just write multiplication. Wait, this iPad is not working. Now I just want to write multiplication. Okay, let us go for multiplication again. Just give me a second. Some problem may be there here in the product. Now this is multiplication. I'll first write multiplication. not working. Yeah, it's working. Now this is multiplication. Now we will go for next is dot product. Okay. And the last one we are going to define is inner product. We are going to define as inner product. For this, we will see the properties. What are the properties possessed by the previous definition? The first property possessed by the multiplication is symmetricity. Then we can show linearity. Okay. Then this is homogeneity. And last is positivity. Okay, I'll just minimize. Positivity. Okay, what is multiplication? Symmetricity means if I take any two scalars, then alpha dot beta is beta dot alpha. Right? No, alpha dot beta is beta dot alpha. Okay, and here next is linearity. What linearity tells me? This is if alpha plus beta into some gamma, then this is alpha dot gamma plus beta dot gamma. This is called as linearity property. And what is homogeneity? If we have some three scalars, alpha beta into gamma, we can write as alpha into gamma. And what is positivity? If we multiply a scalar with itself, that is alpha square, this must be greater equal by 0. That is alpha dot alpha is equals to greater equal by 0, and alpha square is equals to 0 will implies an implied by alpha is equals to 0. These are the four properties possessed by the ordinary multiplication. Let us see whether the all properties are true in a dot product or not. If we have two vectors u and v in RNA, then in a dot product, symmetricity holds. That is, u dot v is equals to v dot u. This is true. Okay. Next, what about linearity? Suppose we have two vectors, three vectors, u plus v dot w. Then this is defined as u dot w plus v dot w. Similarly, if we have any scalar, say lambda, then lambda into v dot u is defined as lambda v dot u, homogeneity. Okay, and lastly, v dot v is greater equal by 0 or v dot v is equal to 0 implies an implied by v is equal to 0. Okay, now let us go for the property of inner product. Inner product we are going to define with this symbol. Inner product we will define by angle brackets. Okay, therefore if I define, this is no doubt we are considering over Rn only. Okay, therefore the inner product uv is must be equals to inner product vu. First, symmetricity property. Next, u plus v with w, and inner product taken of a vector u plus v with w is defined by inner product u with w added with inner product v with w. This is the property. Now let's go for homogeneity. Lambda v inner product with u is defined as lambda times inner product v with u, and lastly inner product v with v is greater equal by 0 or inner product v dot v is equals to 0 implies an implied by v is equals to 0. See here, just keep the point in mind. This inner product we have defined on Rn itself only. We are not considered the complex space still. Okay, therefore this is what properties possess. Now we are going to extend multiplication to dot product to an inner product. I hope you have understood why the need of an inner product, because in complex spaces, for complex spaces we will not define anything. For dot product, what is the use of dot product? With the help of dot product, we will be able to find out the length of a vector and the angle between the two vectors. Right? The geometrical properties of the two vectors we can obtain with the help of a dot product very easily. We are extending the same to complex numbers as well with the help of inner product. Therefore, I hope you have understood both the definitions of dot product I have explained in the today's lecture. That is by definition mod x mod y cos theta and piece by piece itself. And these are the properties of the product. And this is what inner product we are going to define with the help of an angle brackets. Possessing the properties symmetricity, linearity, homogeneity and positivity. Okay, with these introduction, let us go to define inner product. Okay, so now it's a time to define inner product. As in the Banach spaces, we have extended metric to norm. Therefore, in the Hilbert spaces, we are extending dot product to inner product. Right? Therefore, if I want to just tell you what is an inner product is the generalization of a dot product. In the vector spaces, it is a way to multiply vectors together with the result of this multiplication being a scalar. Inner product allows the rigorous introduction of intuitive geometrical notions such as length of a vector, angle between the vectors, and inner product is the generalization of the Euclidean spaces. Therefore, we'll just try to understand what is the definition. Okay, the inner product is defined as let X be a vector space. Okay, then and F be a field. The field may be real numbers or the field of complex numbers. Okay. Then an inner product on X is a function. An inner product on X is a function denoted by this angle brackets, which is a function from X cross X to field which satisfies following properties. Okay, the first property of an inner product is inner product X with X is greater equal by 0. Okay, second property is if inner product of X with X is equal to 0, this implies and implied by X is equals to 0. And the two property together is called as positive definiteness. Okay, next third property is if inner product X with Y we have, then if we take a conjugate, this will be Y, inner product Y with X. This is called as conjugate symmetry. In previous introduction, I told you about symmetry only because we have defined this whole on a RNS space itself. But now this is defined on a complex space as well. Then therefore it will be a conjugate symmetry as a third property. And the fourth property, where here the bar denotes the conjugates. Okay, fourth property is inner product alpha X plus beta Y together with Z is defined as alpha times inner product X with Z plus beta times inner product Y with Z, and this property is known as linearity in first variable. Or first coordinate. Linearity in first coordinates. Okay. Therefore, if you just have a look to the previous concepts I told you, symmetricity, linearity, homogeneity and positivity, same definitions, same concepts was taken as the axioms on the inner product. Okay. Therefore, first thing, inner product is a function defined in the Cartesian product X cross X because we need two vectors for the multiplication and the resultant must be a scalar. Therefore, the codomain must be a field which satisfies the properties. First property and second property together will give us the positive definiteness. Third property is conjugate symmetry. That is a product, inner product x with y is conjugate of inner product y with x. Okay. Then fourth property is linearity in first variable only. With these, any function is satisfying these four properties is known as an inner product, and a vector space, linear space together with this inner product is known as a inner product space. Therefore, here I will write IPS, inner product space, a linear space X, a linear space X together with inner product is called inner product space, is called as inner product space. And actually whatever the topic name I told you, a Hilbert space, is nothing but a complete inner product space. Hilbert space is nothing but complete inner product space. The concept goes very parallel to the Banach spaces. In Banach spaces, first we have defined non-linear spaces, and later the complete non-linear spaces are the Banach spaces. On the parallel line, here we have defined inner product spaces, and complete inner product spaces are nothing but the Hilbert spaces. Okay. If the underlying field is a real field, then this is known as a real inner product space. If the underlying field is complex space, then this is known as complex inner product space. Okay. And the inner product of a scalar is a inner product of two vectors is a scalar. Okay. Therefore, today I just want to show you who is the Hilbert. Okay. So let me just stop this screen and I'll share you. I hope it is visible to you all. Therefore, he was a mathematician, David Hilbert, who has introduced the concept of Hilbert spaces. We'll just try to understand the life history about him. He was a German mathematician, born on 23 January 1862, died on 14 February 1943. He was one of the most influential and universal mathematicians of 19th and early 20th century. He discovered and developed a broad range of fundamental ideas in many areas, including invariant theory, calculus of variation, commutative algebra, algebraic number theory, foundations of geometry, spectrum theory of operators, and its application to integral equation. If you just read those lines, still it will give you a variety of the mathematics papers. Okay. This was a photo. David Hilbert. He looks like a handsome guy. Okay. He was having a nationality of German, and he is having many doctoral students. One of the doctoral students to note here is Newman. We know about Newman. Okay. Von Neumann, we have seen many theorems defined by Newman and all. Okay. So this was a brief history about mathematician David Hilbert. You just go with this because I am telling you always, it was always interesting to know about the life history of the mathematician, because it gives an inspiration to all of us. Okay. Therefore, in the next lecture, we will go for some important theorem related to inner products, and we will try to understand what is the definition of the Hilbert space, as well as I told you a definition today. Complete inner product space is the definition of the Hilbert spaces. Therefore, from today onwards, we will take the live lecture and we will make the recording as well. Live plus recording, because I have noted that no one from you has seen all the lectures of function analysis I shared with you recorded. Therefore, from now onwards, we will take a live lecture, live plus recording, as we have 40 minutes time for the Zoom recording, right? Now, one important thing to tell you is, in the next lecture, we will take a test on Banach spaces. Okay, up to Han-Banach theorem will be the syllabus. I have declared this in the last month itself, but as you are having some backlog exams, I hope all the backlog exams are now completed. Therefore, in the next week, be ready up to the syllabus of Han-Banach theorem, including Han-Banach theorem will be the syllabus. So I will take the test of 20 or 30 marks. Okay, and probably it could be a multiple choice questions only, but detail I will tell you later. Okay, so thank you for being with me for the today's lecture. I hope you have understood today's lecture. If you have any difficulties, you can please raise the difficulties to me. Okay, thank you for being with me for the